Consensus is the trust engine of a Besu network. It determines which blocks are valid, how transactions are ordered, and what state everyone accepts. In this module, we'll compare QBFT, IBFT 2.0, and Clique through finality, governance, and fault tolerance. You've already built the core Besu foundation: what Besu is, which network models it supports, and how its nodes are structured. Now we'll connect those pieces through consensus, where nodes agree on ledger state and block production. If every node keeps its own copy of the ledger, who decides the truth? Consensus provides that shared decision process. It turns proposed blocks into accepted records, even when some participants fail, disconnect, or act maliciously. Block creation begins when the consensus rules select a validator to package pending transactions into a proposed block. That proposal is not trusted automatically. Other validators check the block format, signatures, transaction validity, and whether the proposer was allowed to create it. Once the required threshold agrees, consensus is reached. The block is committed, shared across the network, and each node updates its local chain. Finality is the point where a transaction stops being merely recorded and becomes safe to rely on. In probabilistic networks, confidence increases as more blocks are added, but some reorganization risk remains. BFT-style consensus works differently. Once enough validators commit, the result is treated as deterministic. For enterprises, that matters because payments can settle, audits can trust records, compliance steps can trigger, and systems like ERP platforms or APIs can automate work without waiting for uncertain confirmations. Besu's consensus role depends on the network you are building. In permission networks, the chain usually defines its own block production rules. QBFT is the modern recommended BFT option. IBFT 2.0 is similar and remains common in older Besu deployments. Clique is simpler proof of authority, useful for development or tightly controlled networks. On public Ethereum, Besu does not run consensus by itself. It serves as the execution client, paired with a consensus layer client. IBFT 2.0 is designed for permission networks where validators are approved and accountable. One validator proposes a block, and the others vote on whether it is valid. When enough validators agree, the block is committed with deterministic finality, meaning it will not be reversed. Its key safety rule is quorum. The network can tolerate faulty or malicious validators as long as fewer than 1/3 are Byzantine. That makes IBFT 2.0 well-suited to consortium environments. QBFT is Besu's modern choice for Byzantine fault-tolerant consensus in permission networks. It gives enterprise applications deterministic finality, so committed blocks are not later reorganized. Validators are known participants, and membership changes happen through voting rather than open competition. The result is predictable governance, resilience against faulty or malicious nodes, and a practical default for new consortium deployments. IBFT 2.0 and QBFT address the same core need: validator-based consensus with deterministic finality in a permission network. The difference is mostly practical. For a new Besu enterprise network, QBFT is typically preferred because it aligns with current recommendations. For an existing IBFT 2.0 network, staying with it can be reasonable when compatibility, operational stability, and governance continuity matter more than changing protocols. In BFT systems, the validator set is the trust boundary for consensus. If fewer than 1/3 of validators are faulty or offline, the network can usually still agree safely. Validator count, however, is a trade-off. More validators distribute power and improve decentralization, but they also increase communication overhead and create more opportunities for downtime. Too few validators are easier to coordinate, but they concentrate governance risk. The goal is not maximum size. It is enough independent, reliable validators to keep quorum available under stress. Clique is proof of authority with a practical goal: make a private Ethereum-style network easy to run. Instead of mining, a fixed set of approved signers takes turns creating blocks, so block production is fast and configuration is simple. That makes Clique useful for internal development, smart contract testing, demos, and other low-risk environments. The trade-off is security depth. Clique does not provide the same Byzantine fault tolerance as QBFT or IBFT, so avoid treating it as the baseline for regulated, high-trust consortia. Choosing consensus is an architectural decision, not a simple toggle. Start with the trust model. Who validates, and what failures must the network survive? If you need deterministic finality and Byzantine fault tolerance, BFT-style consensus is usually the right fit. If the network is small, trusted, and speed matters more, Clique may be enough. Then test the choice against governance, validator onboarding, latency, monitoring, upgrades, and recovery. The best mechanism is the one your organization can operate reliably. Consensus choice is less about finding a universal winner and more about matching constraints. For new permissioned enterprise networks, QBFT is usually the safest default because it combines strong finality with robust fault tolerance. IBFT 2.0 still matters when compatibility or an existing deployment drives the decision. Clique is useful for controlled labs, demos, and lightweight environments, but it should not be treated as the production security baseline. In production, consensus is not something you configure once and forget. It has to be operated as a living control system. Continuously watch validator liveness, block production, peer connectivity, and consensus errors. Protect validator keys with strong storage, limited access, and clear recovery procedures. Define who can add, remove, or replace validators before an incident occurs. Finally, test failures deliberately, including node outages, latency, and upgrades, so the network's behavior is known before business continuity depends on it. Consensus is where enterprise blockchain design becomes real. Nodes agree on valid blocks, ordering, and shared state. In Besu, QBFT, IBFT 2.0, and Clique each trade-off finality, governance, performance, and complexity. Next, you'll use those choices to shape topology, node roles, permissioning, privacy, and enterprise patterns.